All right. Good morning, everyone. Hope you all had some time to get coffee, breakfast, have some good early morning energy going. I'm very glad that you made it all the way out to Friday, and thank you for attending this session. This session is all about our supercomputing infrastructure. We're going to walk through how we're building out the fundamental infrastructure that powers all of the AI revolution that's happening today. My name is Nitin Nagarkatte, and I am a product manager at Azure, focusing on our AI compute technologies. And presenting with me today are going to be Hugo Affaticati and Klaus Jorgensen. And Hugo is our senior infrastructure engineer working on really cranking up these machines to deliver the most performance they can. And Klaus is our storage expert who builds a lot of cool technologies that really power all of the storage that's needed to build and deploy large AI models. So let's get started. This is what we're going to be covering today. I'll begin with a little bit of basics of, hey, what's going on in the industry? What is it that we are actually trying to solve here? And from there, we'll go into a deeper dive of the actual supercomputing infrastructure that we're building at Azure. And from there, we'll transition off into a little bit more deeper dive into the storage technologies and the training performance benchmarks that my teammates here will talk through. So let's get going. Obviously, AI is everywhere. You've made it through the week here. You've seen AI in pretty much, I think, 80% of the talks that happened here. It's touching pretty much every aspect of life today, whether it's healthcare, whether it's drug discovery, self-driving cars, you name it, and it's happening. And all of that really requires a huge powerhouse of infrastructure that enables the work that eventually powers the end user experience that you're seeing here today. And we are going to be talking about exactly that. So let's begin with a little bit of a history of model evolution. Again, this should not be a surprise to anybody. All of this really began, let's say, 2019, 2020 timeframe, when the GPT model kind of made its presence felt on the world stage. At that point, the models were all text-based, chatbots, kind of rudimentary in terms of what they were able to do. And on the left axis here, I'm just showing how big these models are, right? Just to kind of provide some emphasis on what's happening in the technology behind the scenes. From there, 2022 is when ChatGPT really went mainstream. This was kind of the big ChatGPT moment. Everybody was talking about it. Everybody was using it. And the models were still in these 100 billion parameter type range. Going forward from there, multiple revisions of ChatGPT came out, others in the industry joined in, llama came out, Cloud came out, and we started to see models actually grow in complexity quite a bit. So they went into hundreds of billions of parameters. And from there, last year, it was all about multimodal models, long context models, being able to solve real use cases for enterprise, setting up workflows that actually result in value to enterprise customers. And this year has obviously been the year of agentic workflows. This obviously requires much more complex models, and these models now range in the trillions of parameters. So literally in a short period of 5 to 6 years, we've gone several orders of magnitude up in terms of the complexity of the models that we need to build and deploy on our infrastructure. So I'm going to give a little bit of a walkthrough of what Azure has been doing in this space. Azure has had a long history of working with our HPC partners in building out high-performance computing. And back in 2019, 2020 is when we really started thinking about building this at scale. This is what really powered some of that early research that went into the GPT models. Azure was the first in the cloud to actually build a capability to run workloads across about 80,000 cores back in the day. Seems not so big now, but that was a huge accomplishment. Lots of work in back-end engineering, connectivity across all of these capabilities. And at that point, just for fun, we kind of went and measured ourselves against world supercomputers. And this was basically a top 5 supercomputer without us intending to go after any supercomputing benchmarks. This is really what the first GPT models were built on. From there on, we've been kind of just evolving constantly. Again, for fun, we keep comparing ourselves against these large supercomputing deployments happening all over the world. And the fact that this is happening in the cloud means that all of this is easily accessible from anywhere, fungible, which is not necessarily true when you do true supercomputing. Back in 2023, again, we looked at what enabled GPT-4. This was still the number 3 supercomputer in the world. One thing to note here is that all of this is still happening in the Azure cloud, so you can still access it from anywhere. It's scalable and has all the benefits that come with cloud deployments. Most recently, the GPT-5.1 models, which were kind of the latest that were released, have been built on clusters that deploy the latest generations of GPUs. We have large clusters of GB200 and GB300 GPUs, which are the flagship GPUs from NVIDIA in the current stage. We'll talk a little bit more about what goes on behind the infrastructure, but this is just a little bit of a historical view of how this has evolved. So to begin with, that 2000-2001 supercomputer, we nicknamed it Eagle, and as I mentioned, this was among the biggest in the world at that point. From there, we evolved to a stage where we're literally deploying equivalent of 1 to 2 supercomputers every week. So I'll take a pause and let that sink in. This used to take years to deploy, not so long ago. We are at a stage where my colleagues right now are sitting somewhere trying to deploy the next supercomputer, and we literally push out 1 to 2 of them every week. And these really go into powering a lot of the fundamental model research that's happening today in this world. We recently made some announcements around our Fairwater infrastructure. Fairwater is basically the largest training site imaginable, hundreds of thousands of GPUs, and it's roughly, depending on what metric you use, 10 to 15x the size in terms of the amount of compute that's packed into one fully connected supercomputer. I'm going to take a pause and let this video speak for itself. So this is just a quick clipping showing our second Fairwater site that we just announced last week, which is in Atlanta, Georgia. The first one was in Wisconsin, and this is kind of our extension to that. And these are all connected by AI WAN with, I think, like 1,500 terabits or insane amounts of network capability. Going forward from there, just want to kind of pivot to what are some of the fundamental layers that power all of the work that happens in this space. The very basic layer is what we've been talking about all along, the fundamental infrastructure, the hardware, the compute, whether it's CPUs or GPUs, the network that binds all of them together, and the storage that actually feeds them with information. Above this is our fundamental AI platform. So this is where a lot of the virtual machines, virtualization, orchestration, scheduling, all of these happen here, along with then combining these with standard frameworks like PyTorch, to ensure that our researchers can actually build stuff. On top of this, Azure also provides a lot of managed services. So these may be much more relevant, not so relevant when you're trying to build a frontier model with hundreds of thousands of GPUs, but much more relevant when you're trying to build some specific use cases in the enterprise setting. Azure Foundry has, I think, somewhere around 10 or 11,000 models at this point supported. And the Azure AI Studio really provides you kind of a playground to play around with all of these capabilities and build what you need in this space. And finally, on top is basically what is the final customer-facing view, which is various kinds of co-pilots, agents, assistants, whatever it is that you want to build. So let's take a deeper dive into that training infrastructure, which was basically the foundational layer on which all of this is built. So this is our product roadmap across various technologies. On the top is obviously GPUs, because that is kind of the fundamental building block in all of this today. We also talk about CPUs because a lot of prep work, data cleaning, ETL, et cetera, actually happens on CPUs even before this gets to the large GPU clusters. And interconnect is a fundamental requirement, because if you want to train across 100,000 GPUs, they need to be connected with the right amount of connectivity there. And none of this works without storage, so hence storage as well. So on the GPU front, I'll just kind of go row by row. We obviously work very closely with NVIDIA. They're one of our closest partners. And we co-innovate with them to ensure that we are building the right kind of solutions for the next generation of models that needs to be built out. So we've been basically every year or almost every 6 months deploying a new generation of GPUs with incremental capabilities, sometimes 2x the compute, sometimes 2x the network, or sometimes combinations of those. So just earlier this week, in one of our keynotes, we actually announced that GB300 is now generally available. This is the flagship product that's available in the industry today. And Azure is the first cloud to actually go deploy this at scale. We already have close to like 100,000 GPUs deployed, and we're continuing to kind of build that scale out. We're also going to be building out the next generation. So coming out next year is going to be our V7 generation with the next generation of GPUs. So all of this layer, the top layer is where the foundational models are built. So these are where the 100 billion parameter models, the trillion parameter models are actually built, because that's where the capabilities lie. The next row talks about our PCIe-based solutions. So this is where if you're doing small model training, inference, also want to potentially mix and match with some virtual desktop or other kind of use cases, this is where you would go. On the AMD front as well, we've been partnering with AMD for a long time now. We have their MI300X, which is out, and then we're now working on 455, which is their next flagship product. Looking at the CPU world, we've done a lot of work in building out HPC-specific, HPC-centric CPUs as well. These typically powered by AMD because they seem to have the best capabilities in the world today. And we see actually a lot of traction on these across spaces that are more HPC-centric, but more recently in the last few years, we see these are being used more and more in the data prep pipeline for AI models. So the exabytes of data that needs to be pre-processed typically runs on these kind of CPUs. On the interconnect front, we've partnered again with NVIDIA to build out the latest generation of InfiniBand and really deploy it at scale to hundreds of thousands of GPUs. The NDR generation was what we had until pretty much earlier this year. We are now on XDR, which is the latest generation, about 800 gigabits per second of bandwidth per GPU. Again, this is critical because when you're trying to train models and do all kinds of back and forth across the GPUs, you need to make sure that the GPUs are never starved and waiting for information. We're also building out some Ethernet-based technologies, and we'll talk more about them in the near future. And finally, on the storage front, Azure has been pretty much at the frontier of what's possible in terms of storage capacities and bandwidth. And we're basically looking at over 6 terabytes per second of capabilities coming up early in the next year. We're going to talk a little bit more about these in Klaus's section as well, so I won't go into that in detail. So just to summarize, GB300, our flagship product for large-scale models, is now GA, and the NCV6, which is basically our universal compute for small to medium models and other workloads, is now in preview. So I'm going to dig a little bit deeper into those ND series of technologies, because this is really what is powering all of the fundamental models that we are looking at today. So the fundamental building block here is the GB200 or the GB300 super chip. So this is one Grace CPU. It's an ARM-based CPU combined with 2 GPUs, Blackwell generation of GPUs from NVIDIA. And there's 2 of those now. So there was B200 earlier in the year, and now we are on B300 generation. These are combined together in a tray, a compute tray, and we add some more goodies like Azure Boost technology to essentially offload virtualization kind of capabilities from the GPUs themselves or the CPUs themselves. And this whole unit forms basically one virtual machine. So this is, if you ever go deploy one single node of this, this is what really you're running on. We stack 18 of these together in a single rack. So and connect all of those together with high bandwidth NVLink, 1.8 terabytes per second of bandwidth connectivity. So effectively what's happening here is that entire rack is becoming one computing unit with a shared memory pool. So this allows really large models to fit in there easily And for any of the workloads that you're trying to run, training or inference, to any GPU there can actually access memory from another GPU somewhere in the rack at very high bandwidth, really enabling high performance and high efficiencies. And finally, all of this combined together with our backend technologies, our InfiniBand technologies, and scaling out to data center scale, hundreds of thousands of GPUs. Let me go to the next slide, which basically talks about our backend network a little bit. As I mentioned, state-of-the-art network is fundamental. We cannot have these expensive GPUs waiting or idle. So ensuring that there is no bottleneck in data passing back and forth is critical. That's why we've done a lot of work in building out this dedicated backend network. This is based on the latest InfiniBand technologies and is a completely non-blocking fat tree topology. So what that really means is every GPU can talk to every other GPU at line rate. There is nothing blocking in between. What this translates to is super low latencies, so about 1.5 microsecond latencies between GPUs. And of course, all of this network is backed with a lot of goodies in terms of offload mechanisms to ensure that the network only has to focus on the critical paths and nothing else in terms of management, et cetera, and various other optimizations, adaptive routing, and so forth. Imagine all of these capabilities, again, at a scale of data centers where literally hundreds of thousands of these GPUs are connected together. That's really what is driving performance today. So I touched upon two aspects of cloud, compute and network. The third critical pillar here is storage. And I'm going to invite my colleague Klaus to come talk about storage and walk through what is it that we're doing to really improve performance there.
Thank you, Nitin. And I hope you enjoyed this morning and made it through Friday all right. So let's take a look at the storage-centric view of doing training and fine-tuning in Azure. Our customers, including our large customers like OpenAI, generally follow this process that I outlined here at the top of the slide. It starts with ingestion. Ingestion is really about acquiring data and then getting the data into the system in order to do the rest of the work. This, depending on the ambition of your project, this could be tens or even hundreds of petabytes of raw data that is then moved into the Azure cloud. Next step is that we need to prepare the data for the actual training itself. And there is two sub-pieces to this. The first part is to clean up the data, so that means removing the noise, removing the elements of the data that we don't really need in order to train. The second part is the data preparation, where you go in and take the rest of the data, you tokenize it, you augment it, you annotate it, and all the pieces that needs to be done around that data in order to prepare it for training. This process actually takes that original data of potentially hundreds of petabytes and ends up with typically hundreds of terabytes of data being consumed. Once that is in place, this training data is then pushed into the training pipeline itself, which is where the GPUs come in that we just talked about. All the other left pieces are done on CPUs typically. During this process, storage really supports two base functions. One is the shared platform for which all the GPUs read in the data to be trained on. And the second part, during the training portion, the job will checkpoint data out to be able to recover, come back in time if we have a GPU node failure or a GPU failure in itself, or if it needs to read some of the data for fine-tuning later on. And then all that checkpoint data actually, because there's so much of it, that actually explodes into petabyte and even exabytes of data that is being generated doing this. And at the end of the day, we end up with a model that then can be used over in the inferencing that we talked about on Wednesday. So take a look at specifically on the storage details on this. So on the ingestion side, most of it we see is ingested just over the network, which is a massive undertaking of itself, moving hundreds of petabytes over the network. But there are also other products like DataBox if you need to move data offline. In the training and preparation, that is typically done by analytics frameworks like Azure Databricks or open source Spark, etc. In this case, it uses our ADLS Gen 2 storage platform, which has a hierarchical namespace that is used by these frameworks. The most extreme part in terms of performance is really around the training portion. So the first part is most of the tooling in the training is actually written to use file systems. And then you have blob storage on the back end being the massive capacity and high performance. So what we typically do here is we use tools like BlobFuse, which does a torque conversion between the file system and the blob storage. Essentially, you can think of it as mounting the blob storage container into the local Linux file system, so all the tooling just works. Right? The conversion is taken care of by BlobFuse. For the actual throughput, whether it's the reads of the training data or the writes out of the checkpoints, we're using the scaled accounts that you might have heard of. This scaled account is essentially the technology that we developed to meet the needs of the massive scale that is required by these workloads. Right? So AI and the training of AI had pushed the requirements like tenfold over the last 3 to 4 years, and we don't see that stopping. So we keep pushing the frontiers, and I have a little demo for you after I'm talking with this slide. And then once you create all these checkpoints, you have all this data out in blob storage. When you no longer need massive performance on it, you can then use the data management toolings as well as our various storage tier to push that data out into colder storage to reduce the overall capacity cost of the solution. So you keep the data that needs the best performance in the suitable tiers. All right, so what I want to do next is I want to show you a demo, but I want to describe the demo before actually running it so you have a little bit of context. So we're using a storage benchmark, comes from the HPC world. All it really does is basically very simple to massively scale out and do massively parallel reads and writes from a file system or a storage system like Azure Blob. We're using Azure Cycle Cloud as the workload orchestrator. For all intents and purposes, you can ignore that. But we use that to stand up, in this demo, 700 clients, 400 for reads and 700 400 for writes and 700 for reads, consuming roughly 100,000 CPU cores. That's the other benefit. This framework doesn't require us to use CPUs, so it becomes a little less expensive for us to run this. And then, of course, as I mentioned just before, we're mounting the blob storage using BlobFuse, and we're actually going to write 1.5 petabytes of data, and we're going to read that data back and take a look at what that looks like. So first, we're going to stand up, I'm going to start this. We're going to stand up our storage cluster. There is the 480 nodes. The storage cluster, the compute cluster is created. We're going to look into that, and then we're going to see the configuration here. You highlighted the BlobFuse that is mounting on the core storage container called training data. Now we're going to actually use the IOR framework to push the write portion of it. So here we're firing up the nodes, the 480 nodes, running a total of 11,520 tasks, all just writing data. So what you see here on the right side is the write throughput, and that peaks out at roughly 22 terabits a second. That is just shy of 3 terabytes per second of writing data out. And this is sustained over several minutes in this particular benchmark. Now we'll switch to the read side. And on the read side, we stand up a separate set of compute nodes to make sure there are no caching effects. These computes have not been involved in the writing of the data. 695 compute nodes, and then we're reading. And on the read side, we hit over 51 terabits a second of throughput, or more than 6 terabytes a second of throughput here. If you want an analogy to this, a 4K video stream unbuffered is roughly 50 megabits. So this corresponds to running roughly 1 million of those streams in parallel out of a single storage endpoint. So to put this in context, here's the simple numbers that makes it a little easier if you want to take a picture of it. The 22.2 terabits a second of writes and the 51 terabits a second of read. And just to see how the industry is moving here, this is today. 6 months ago at Build, it was half this, or actually this is 2x what we showed at Build just 6 months ago. And that build was doubled based on the prior demo. So we basically quadrupled the amount of bandwidth that we support out of these storage systems in about a year time frame. And also to make sure that you fully understand this, this is actually what some of our customers are operating at in production in our clouds today. Thank you. I'll hand it over to Hugo for the remaining part.
Thank you, Klaus. What an achievement, isn't it? Good morning, everyone. As we discussed, Microsoft Azure is running some of the largest GPU supercomputers and AI factories in the world for the frontier models. At this scale, supercomputers work like one giant machine, where if one NVLink domain or one GPU is down, then the entire training efficiency is down, is degraded by the performance of the worst item. So in this context, the entire industry runs health checks. A health check, see it as a grocery list of making sure that the hardware is alive. It would be, is the NVMe disk mounted? Is the NVLink domain connected? Is the GPU, the number of GPU on the virtual machine correct? At Azure, we do something slightly different. We have another step, which is performance validation. It goes a little further because it ensures that the entire supercomputer is not only alive, but it's also efficient and performant. And there are two techniques for that. The first one is to do pre-validation. By using a small model, and in this case I'm presenting with the 𝗲𝗲𝗀𝗏𝗏𝗏𝗏𝗏𝗏, which is also a mixture of expert model, which means that it has the activation checkpointing and the multidimensional parallelism. So it is representative of workloads. By its size, it allows us to target and stress specific items in the supercomputer. This is very useful for supercomputers that are used across different models. So if you're thinking about validating a specific subset of nodes, then pre-training models are a great tool. On the left side here, I'm showing examples of varying the batch size. Varying the batch size will vary the amount of memory of the GPU that's being used. So it will specifically target the GPU memory and the GPU utilization. On the other side, for a constant batch size but changing the parallelism, you will force the communication within the NVLink, which would, for the same GPU utilization, vary the training time and creating an overhead just to stress that communication, as I was mentioning. If you want to learn more about any specific item that I'm presenting about, we have those QR codes to double-click on performance and have a better understanding of what is the strategy behind and how we run the tests. So outside of small-scale validation, we also do large-scale validation, which would be a full-size training model. Here, we use the GRAC 314 billion parameters to run on hundreds of racks in the data center. GRAC is a mixture of expert transformer, so training it stresses both the forward and the backward path, unlike an inference workload would. As a mixture of experts, only a subset of experts are being activated per token, which generates dynamic communication patterns across GPUs, which best represents large model that you might be running on Azure. This type of test tests both the compute and the communication. For the compute, the GPUs, the CPUs, and for the communication, it will be both the NVLink and the Ethernet or the InfiniBand. But what it also does is check the hypervisor and the image quality, something that people tend to forget. On the right side of this, for example, is the difference in one very easy setting, which is the CPU governor setting. If you're a little familiar about the governor setting, there are different clock frequency at which the CPUs can send tasks to the GPU. And by having it on demand versus of performance, you will not see the same training time. And what you see here, the big drop is going from on demand to going to performance, where the performance drastically improves because the training time per step of the model decreases by more than 20%. We run those jobs uninterrupted for 24 hours. What we have realized in our tests and our studies is that a lot of the errors and a lot of the issues that you would see with your training job happen in the first 24 hours. That way we get out of the way all the GPU, the misconnections, the thermal issues by looking into the telemetry and the performance of the cluster itself. And the second reason for running for 24 hours is that a lot of the hardware takes a moment to reach the stability of the cloud, stability of the power, stability of the temperature, as you can see on the left on the curve. And so running at steady state ensures that the performance will be delivered for your actual training jobs at steady state. Those were the latest on the GB200 and GB300, so that Blackwell generation of NVIDIA GPUs. But we're also aware that some customers are still using the H100 and running not already agentic AI, but running maybe some multimodal or running some large language models. What I'm showing here is that two things. First, the process that we follow to train is very similar to validate, is very similar to the process that you use to train. It means that we deploy our virtual machines, we deploy our storage, we then add our orchestrator in the example that both Klaus and I have been sharing has been using the Cycle Cloud. Many of you may be using Azure Kubernetes services. Then, like any player in the industry, we run the health checks, making sure that everything is connected correctly, the list of the GPUs, everything is correct, and then we run the performance validation. The last step being yours, being selecting your model and creating your application based on it. On the H100, we're using the Nemotron 340 billion, which is using another data type, which will be FP8 here, in comparison to VF16, for example, that we could do with the GRAC 314 billion. And what we do see is two very important things to remember. The first one is the scaling, and the second one is the difference between a baseline that we are having from our partners running on-prem to what we do in the cloud. Like I was mentioning before, running on the entire cluster allows you to flush out all the hardware and inefficiency, but also validate that your image and validate that your hypervisor are working correctly. And what we see is less than 2% difference between on-prem and our Azure virtual machines. And then for the scaling, as I was mentioning, from 8 GPUs to 1,000 GPU is a 95% scaling. And if we look really into the performance of our network behind it, is going from those 8 virtual machines to, 8 GPUs to 1,000, is that 95% scaling of the Nickel library. How do we get there? Well, there are a couple of things to be aware of. Two main things. The first one is there is a difference between having 1 NIC for 400 gigabytes and 4 NICs with 100 gigabytes each. There is an overhead, there is a non-negligible overhead in multiplying the number of NICs. That's why we have partnered with NVIDIA on the InfiniBand, because it removes that overhead and really makes the network being a support to the GPU and not a bottleneck to the GPUs. The second thing is, as you've realized by now, we do our own studies and we make sure that the performance work out of the box. For that, I'm sharing here a list of 6 very important Nickel exports that make the Nickel library and the communication be very efficient on Azure. While those exports are very important, and I recommend you to make sure they are being used in your training job, they are already implemented in the topology and in the Nickel library that we build and we put on the Azure image so that you have performance out of the box. and that performance being 95% scaling all the way to the scale of 10,000s of GPUs. So today, we discussed the industry standards and how we at Azure offer compute, GPUs, network, and storage to make the biggest AI factories in the world connected together with the AI one. We've also talked about size, how year over year, the capacity that we deliver grows 15 times, and about year over year, the performance is improved at least 2 times generation over generation. We've optimized our hypervisor, we optimized the performance, we optimized the efficiency so that you can work from hundreds to thousands of GPUs together. And then all of the stack is optimized, so it's not just the hardware, but it really is the entire environment. Thank you very much.